Hello everyone, it's December 31st. Alright. About a 1 hour to midnight to New Year. Let's just do this. We got an easy one today. So maybe we just go, do I have Ghana to do this? Probably not. And this is still fresh in my mind, so I probably don't want to do it now. This as well. So all these problems will probably save for, for another time. At least not right now. Not right now. So now these two. This one I don't have the Ghana to do. I don't want to do this. So yeah, definitely. All right, we're gonna do a couple easy ones today. It's New Year. All right, assign cookies. Assume you are an awesome parent. Want to give your children some cookies, but you should give each child at most one cookie. Each child has a greed factor, great, which is the minimum size of a cookie that a child will be content with, and each cookie j has size sj. If sj is larger or equal to gi, we can assign a cookie to child and the child will be content. Your goal is to maximize the number of your content children and output the maximum number. Okay. So in this case, I can only satisfy one because the other two kids have more desire than what the cookies are allowed. You can only make one child. In this case, I can make two. Right? I have 1 and 2. The greed factor is 1 and 2. You have 3 cookies and their sizes are big enough to gratify all. Okay, so basically what we want to find is, so we have a bunch of values here and we want to find how many values in S that can be larger or equal to the value here. So yeah, we can sort, right? We can sort G. Maybe, yeah, we sort G, right? And basically the largest should fit the largest. Okay, we'll sort G and we'll sort S. And then we have 2 pointers. So point from right to left. And then we compare the biggest on the G and the biggest on the S. If the biggest on the G is smaller or equal to the biggest on the S, then we move both forward. If not, then we move the G forward, right? So basically the ideal is we always use, so that the biggest cookie is to satisfy the kid with the biggest greed factor that can be satisfied. Okay. That sounds logical to me. Sounds very logical to me. Man, I didn't do anything today. I was supposed to do some coding, but got lazy. I'm just like, yeah, it's New Year Day. I mean, it happens. So we'll sort this and we'll sort S. Right, we can have for int I equal to, let's say, g dot length, minus 1, I large equal to 0, I minus. We need to do this because we have to go through every single kid, right? And then we say int j equal to s dot length minus 1, right? All right, if gi smaller or equal to sj, right? If that is the case, we need a result. Int res is 0. Right. If that is the case, then res plus plus and j minus, right? Because I use this, so go forward. Otherwise, if it is not g is larger than, then I just keep going. Okay, so we'll do all that and return res. Okie dokie. Take a look. Looks good. Submit. Oh my god. Really? Alright, I hate this. I mean, j has to be larger than 0, and j larger equal to 0. That was such an oversight. It was wrong no matter what, because I shouldn't forget about this. There we go. That was, yeah, it was no oversight. Okay, let's put some comments on this. Let's put a smile on this face. 455. So you count this greedy, right? So make sure the biggest cookie is used to satisfy the kid with the largest desire, largest greed. Right, that's that. But this is OM, so it's fine. That shall be it. Ooh, I need to make a new directory. Holy crap, we're gonna do 2024. Damn. Yeah, we're gonna do 2024. 0 or 2024. Wait, hold a second. What was the underscore 2024 2024 underscore dot Java. Okay, that was good. Greedy 2-pointer, yeah. Sorting and 2-pointer. Yeah, happy new year. All right, so that's it. Right, we're done with today. Let's keep mulling forward. Find the maximum achievable number. You're given two integers, num and t. An integer x is called achievable if it can become equal to num after applying the following operation: no more than t times, increase or decrease by 1, and simultaneously increase or decrease num by 1. Return the maximum possible achievable number. It can be proven that there exists at least one achievable. Okay. X is achievable if it can become equal to num after applying. I mean, if no more than t times, and we can either increase x by 1 and simultaneously decrease num by 1. So we will find this, 4 plus 1 and 6 minus 1. The maximum possible achievable number. Okay, so maximum possible. So the achievable number definitely is bigger than num. Yeah, so you can no more than t times, right? So just num plus t, and then the maximum achievement will go down, right? So basically num plus 2t. Yeah, that's it. Num plus 2t. That's kind of boring, right? Yeah, it's kind of boring. 2769.java. I'll copy this. We say return num plus 2 times t. Oh. Yeah. I always put it like. Alright, let's do one more. Maximum number of jumps to reach the last index. Oh, we have done something similar like this before. You're given a zero indexed array nums of n integers and an integer target. You're initially positioned at index 0. In one step, you can jump from I to any index j such that j is larger than I and the difference between the two is smaller or equal to target. Return the maximum number of jumps you can make to reach index n-1. If there's no way to reach, return -1. Interesting problem. This most likely is just DP. So I'm just going to go right into it. So the first question, the first example, we have 1, 3, 6, 4, 1, 2, right? And t is equal to 2. And we want to go from 0, right? We jump from 0. So we want to find a maximum. So we can say, let's say dp index, right, is equal to the max jumps from 0 to index. So what we want to find is dp n-1, okay? Yeah, the maximum jumps. Therefore, what we need to do is, okay, so what if I want to find this I, dpi, right? We'll find dpi. We'll find a maximum jump to here. Then what we can do is, if I know the max of every single thing, so I can just go back one by one, right? For each thing, for each position, I see how much, and then I will know. So naive solution O(n) squared. Then we're gonna check. So O(n) squared will be allowed. O(n) squared I think will be allowed. So we can try O(n) squared, right? But I feel like there's a better solution, because at each position, we know it has to be within the target, right? So I have a range. We have a range, but you still have to go through every single thing. Unless you can sort it. I doubt it. I don't think you can sort it. Maybe you can, maybe you cannot. But for this one, I think I'm just gonna go straight forward. You know, treat it as a, if this is like when you're going for the contest, like how you're gonna approach it. Yeah, if this is like how I'm gonna go contest, it's definitely O(n) squared, because I think O(n) squared will definitely work, right? So I can even do dp is equal to like 0 steps, right? 0 steps. So maybe we say n equal to line nums. Okay, so this I can times n. All right, and then dp0 is you take 0 steps, right? And then we can say for I in range, say 1 to n, right? And we want to know the number of jumps, and then we say for j in range, the jump to here, so basically it's I -1 all the way to 0. All right, and then for each one, we're gonna say if nums j minus nums I, if its absolute value, ABS, right, is smaller or equal to target, then we can jump from this. So we say dp I plus equal to dp j, and blah blah blah. Then we will return dp, the last one. Actually no, like return this if dp minus 1 is larger than 0, else should be minus 1, unless num's at least 2, right? At least 2. So I think it should be fine. Okay, let's give this a shot. 1000. Yeah, I feel like it should be fine. Oh my goodness, that was terrible. It didn't go all the way to the end. Oh, because I don't have. Oh. This is not right. This should be maybe plus equal to 1 plus. Huh. How many steps to take to jump to the first one? Okay, we start from that is 0, right? To jump onto the second one. So we go to previous. Oh yeah, there's a number of jumps, so it's 1 because you jump to the current. Yeah, my bad. Now it's way too much. What the hell? All right, let's see. The number of ways. So I say the maximum of number of jumps to jump to here. The max number. Oh yeah, that's not right. It's max DPI. That's that. There we go. So this will pass, I think. Huh. I got a wrong answer. Output 1. Interesting. That is interesting. Whoosh. 0, 2, 1, 3. How come I did not get a correct answer for this? Bonkers. Oh, I say I can do this jump because this is 0. If it's 0 way to jump, then it's not possible. Wait, hold on. I can. This is 1. Oh, but I cannot jump from here because it's 0 to here. So this should be 1 because I can jump from here to here. So that's 1. Oh, 3 gets 1 from here. Gotcha. Okay, yeah, that was a logic issue. So if this and dpj is larger than 0, if dpj is not larger than 0, then you can't do. Right? dpj has to be larger than 0. dp I is the max number of steps to go to jump from nums 0 to nums I. One important thing to note is that as we perform DP, if a previous nums j can be used to jump to nums I, yet dpj is 0. That means it is not possible to jump from nums 0 to nums j, which means the jump from nums j to nums I, though allowed, right, by target, is impossible. Yeah, that's the one thing that has to be concerned. Next, is this going to be O(n) squared? All right. Try it again. Oh, wow. That's still wrong. What the hell? Oh, and the j cannot be 1. Oh, shoot. My bad. I didn't even run these. I think these probably is not going to be right either. And, oh. Should be j. So j is equal to 0 is okay. Or how should I put it? J equal to 0, then we do it, right? Or if j is not equal to 0, then this has to be larger than 1. Yeah, I think this one might be right. Oh, that's just poor. This is a very poor performance on this one. Yeah, I know this will pass, but it will be very bad, right? It'll be very bad because there gotta be a faster solution than just. But it's it's okay. So now we can think about if there is a better way to do this. So basically, for each one, we just want to know within the target range, which is basically because this is I, and then this so this plus target or minus target. So we just need to know where it is, which means we can do if we go through everything and then we just record their positions. Yeah. If we record their positions and we always go to the latest one because the latest one will have more steps, right? The latest one will have more steps. Let's say we have duplicate, right? One is at the earlier position, the other at the later position. So we have some step to reach the earlier position, which means to reach the next position will be the same, but we have more opportunities. Yes, I think that is possible. Okay, so let me just redo this. J, so yeah. Okay, so this one is, we use a dictionary. Yes, we use a dictionary to keep track of the index of the last occurrence of a value in nums. right? Then for num's I, we go through the target, right? We go through all possible values in that value that are allowed by target, but depending on how big is the target. Oh no, that is no good. Target is huge, so you cannot go through the target. Holy guacamole. No, this is actually not right. So what I want to know is within this range, who is within this range, right? Who is within this range? I mean, I can use a sorted list. Yes, I can use a sorted list. And a sorted list. So what I want to know is if I have a sorted list, and as I go through the whole thing, I put everything sorted, right? And then when I look into me, I have a range. Then this range allows me. No, all I want to find out is the latest value. That's actually not true. That's actually not true. Because the latest value, you might not be able to achieve it. So yeah, so you have to go through everyone in the previous, but that's still O(n) squared, right? That's still O(n) squared. You just reduce your search. Can we do even faster than that? Like not O(n) squared. So you want to jump, right, to wherever you are. So we want to jump to the last one. Or can we do like a early stop? So basically we want to find a it's not a subarray, subsequence in which each neighbor the difference between each pair is smaller or equal to the target, and I want to find the longest of this, right? I want to find the longest of this subsequence. I don't know. Like, what are the better solutions? Yeah, but it's slow. I have no clue. What would be the better solution? This one doesn't really work. You know what? I should go here and check the really fast ones. What the hell? That is hard to parse. What about these? This is the same. For I, then for J, from the next one all the way to the end, you have to go through every one. So I think maybe they just increase the number of test cases. That's all I can say. That's what I think. Because other than that, at least the general solution, I think that's about it. Two for loops. Two for loops. Everyone has two for loops. But I think that the fast one probably is not. But I have no idea. Everybody has two for loops. Everybody has two for loops. Segment tree. Oh my god. You can use segment tree for this. No, no, no. Just to improve it. I mean, I guess. So how do you do a segment tree? The length of the longest increasing subsequence. Increasing subsequence starts with this, ends with this. Maximum value in the interval. The question change to find the max value in the interval notes. Oh, I think I know what it's trying to say. max value. Why you always say it's increasing though? Yeah, I don't understand this one. Why it says it's the length of the longest increasing subsequence? I don't think this is correct. You know what? Like it's not increasing, right? Yeah, I kind of know. Like you have the current one, so you want to find what value is in this range. But all you do with this is, you find in the previous, yeah, you can within this range, who is within this range, right? So you grab these value out. But when you grab these value out, you still need to know you can't find the maximum. Yeah, this is actually, I think this is not right. Because it says to grab the maximum. I mean, I'm not sure. Oh, it's correct. Oh, yes, because the sequence is not increasing, right? The sequence itself is not increasing, but you can make it into increasing, right? Because the current one, you find the largest within the entire thing. Within the entire thing, you give me this and you find the largest. Why the largest value in this then? Why the largest? Yeah, still doesn't make sense. Nah, I'm gonna be satisfied with this. Yeah, I'll just call this good. Move on. We can do one more. Longest non-decreasing subarray from two arrays. You're given two zero-indexed integer array of length n. Let's define another zero-indexed integer array of length n. For each index I in the range, you can assign either nums 1 or 2 to nums 3. Your task is to maximize the length of the longest non-decreasing subarray nums 3 by choosing its values optimally. Return an integer representing the length of the longest non-decreasing subarray nums 3. Okay, so nums 1, nums 2. One way to construct nums 3. So at each position, you can either assign 1 or 2. Okay, so we either do this or do this, right? We either do this or this to put into nums 3. So we do subarray starting from index 0 and then index 1. Interesting. I think I know what this one is asking for. So we have 1, 3, 2, 1, and 2, 2, 3, 4. Right, we want is the length of the longest non-decreasing. Let's say dpi, okay, is the length of longest non-decreasing subarray ending at I. Right, we can do that. The longest non-decreasing ending at I. Now for I, I have the longest non-decreasing for the previous, right? So for I, my choice is, I have two choices. I can choose this one, right? If I choose this one, then I need to find something like smaller equal to this in the previous. At which position? Yeah, I have two choices. So for each choice, I need to find the largest, right? Find the largest DP value and whose the chosen value can be smaller or equal to the current value. Or you can say yeah, and at a certain position, right? At a certain position previously. At a certain position previously. Oh no, it's not a certain position. It has to be non-decreasing subarray. So it's right in front of you. It's just dpi minus 1. Right? We just dpi minus 1. But dpi minus 1, we have two of them. One is choosing this, and the other is choosing this. Right? So we need to compare the two to know, like, if I'm choosing this, then what is the smallest, the largest? So choosing this, which one is the largest? So we have two DP arrays. We have a DP1 and I have a DP2. Okay, let's say if we have two DP arrays, let's just try to solve this, see if it works, right? So basically we have DP1, right, 0, 0, 0, 0, right? And we have DP2 is also 0, 0, 0, 0. Okay, so the first one, that's always going to be 1. Right, this is going to be 1, this is going to be 1 at the start. DP2 is taking this, DP1 taking this. So now the next position, we can take, if we take 3, okay, then we look to the left, right? This is smaller, so I can do 2. Take this, it's also 2, so the largest will be 2. If I take 2, that's also 2. Now we take this 2. Cannot do this, can do this, so this will be 3. This 3 can do this, so this will be also be 3. Now we take this 1, can take, so ending at this is just 1. 4 can take, so it will be 4. So the answer is 4. Maybe that is the one. Alright, dp1 shall equal to 1. Yeah, because it's always going to be 1. At least is 1, right? Times n. Let's say dp2 is also 1 times n. Right? And then we can say for I in range from 1 to n, right? Because the first one we'll have to do. Then for nums 1, okay? So if it's a nums 1, say handle nums 1. Okay, handle nums 1. If nums 1 I is larger or equal to nums 1 I minus 1, then dp1 I, right, shall equal to dp1 I minus 1 plus 1. If nums1 I is larger or equal to nums2 I minus 1, then dp1 I shall equal to maximum dp1 I and dp2 I minus 1 plus 1, right? If this, then we handle the dp1 I, because dp1 I have two choices. I can compare it to nums1 or compare to num2, right? And then we just pick whichever, right? Pick whichever. I mean, technically you should just do this max as well, but yeah, it's okay because it's the first one. It's the first one. If it just fails, then we just do this, which is okay. And then we have the same thing. We say handle nums2, right? So I'm pretty sure we can yank this whole thing, paste it, and just take that to 2, right? This and this should be nums1, and we say dp1, right? So that should be dp and dp2, right? There should be a dp2. This is 2. This is 2, and this one is 1. Right, once we're done, we return the max. Oh, we have to keep track. Right, no, rest just equal to 0. Right? And every time we're done, we say rest equal to maximum rest dpi and dp1i and dp2i. Yeah, I realized this cannot be, has to be 1. At least we have 1, okay? So we go rest. All right, let's take a shot. Let's see if this is correct. Looks all right. Yeah, that's correct. Create 2 DP arrays in which DP1 I equals to the longest length of non-decreasing subarray ending at nums1I, and dp2I equal to the same concept with regards to nums2. Yeah, that's about it. We call it O2n technically. Okay. Yeah, it's not too shabby, this one. Oof, no. Okay. All right. That'll be it. I think we've done enough. Go on to the next. Yeah. All right. I'll see you guys tomorrow. That's it. Happy New Year. Adios.